We can properly start now. So, as I said, I was here 2 years ago, and I'm going to have a little bit of an overlap today with what I talked about, but I mostly want to talk to you about how to use these operator theoretic techniques in modeling. Although it might not, seem completely that I'm building models at a time, but I will use spectral methods and other techniques to actually kind of build models. And that's what I'm particularly excited about now. And these are both dynamical systems and control models. But before we get there, let's start with a little bit of, you might have seen this particular video. I don't know if you have. If it plays. Have you seen this? Yeah. I don't know if you can hear the music, but Chopin is always good to start the talk with. So, okay, I won't dwell on this. That's where we are. I think generative AI has arrived. Anybody? Not for dynamics, I think. So, in some sense, that's why we're here. It's becoming quite evident that transformers and generative AI in general cannot, at this point in time, capture dynamics very well. Despite some successes, I think Ed spoke about some in climate yesterday. But complicated dynamics like this is still difficult. Let's see something else.
Sorry, for the ones of us who have not seen the video, what was the point of that? That was real, or that was?
Oh, you didn't see how bad it was?
Okay, so it's the fact that it wasn't good.
It was terrible. It starts with some photo and it's trying to produce the gymnastics. But let's see currently what we can do. And I don't know if you can hear the music, but it's my favorite classical composition, which is Bach's cello suite in G, first one. So I will have you watch this. It's a soft robot that is in our lab. You're seeing sensors on it, the LEDs, these dots here. And it has four pneumatic muscles in it. And it's soft. It's a very difficult thing to model. So the operator is the model. What we try to do is generate an operator theoretic model that leads to those equations on the top that you can see, and you have seen them yesterday morning, and we discussed them quite a bit. They're linear, but they're linear in a functional space. They're not linear in state space, clearly. And I'll talk about those embeddings. This is a different one, just so you see that this is robust. And the following of the stick may fascinate you or creep you out, depending on what your position is. But it's clearly quite different from what we've seen in the gymnastics video as far as the execution is concerned. It does have a generative model under it, and it runs on what? 5 watts of energy. So what I would say is this is the benchmark right now. I'll show you the performance values. And then we'll delve into the theoretical side of it, because we also need to have an understanding as to, oh, this is fun, so I'm going to leave it running. It can actually throw balls into... one other thing. If you have heard about reinforcement learning, where the model is learned at the same time as the objective, this actually constructs the model first as it kind of swings around. Think of a baby in a crib and just kind of flailing the arms around, figuring out what the model of its own body is. Figures out the model on the top, and then you give it an objective. So safety first. It's not trying to break things to figure out that it's going to get punished if it breaks, if it breaks things. You give it a training of only the kinds of things that you can do, and I see Eduardo nodding because this is the control theory premise, right? You construct a model, you construct a safe model, then you give it an objective. So, okay, this is what this thing can do. It can catch things and things like that. As I said, I consider this a benchmark. Soft robotics is a great field for us to participate in because very often it's unmodelable. There are no constitutive equations for cloth. Pneumatic actuators, so you're pushing air through the thing. It's not very easily modeled. This is the performance. The methodologies are R and N, reduced order modeling with PODs and so on, LSTMs, and so on and so forth. The numbers at the top are our paper in Science Robotics. The speed is 1.52, acceleration is 11.6 meters per second squared. Deflection is, you saw it, 110 to 180 degrees. These are the deflections in previous papers. This is an order of magnitude less. This is 1 to 2 order of magnitudes less. So we're having between 10 and 100 times improvement on anything that exists in the market with this methodology. Okay. Since it's the Koopman session, I will start with just a little bit of history. I think most people in this room know it, so I will not dwell on it, so it's going to be very short. But because I might run into the time issue, everybody does, I will tell you the main points that I want to convey today. Something that's quite interesting is at parts well known in machine learning and parts has to be re-examined when you do dynamical systems, and that is that the functional spaces, your hypothesis spaces, really matter. So infinity matters is kind of the tag. The other part is, if you're in the classical setting of the Koopman operator, you work in L2 spaces. L2 spaces for measurable dynamics give you everything. And you don't need, and I will repeat, you don't need RKHS, because Birkhoff ergodic theory tells you that the sampling is actually going to give you the correct results. This is a misnomer that has been tossed around, that you need an RKHS in dynamics. You don't. For stationary dynamics, you don't. But off-attractor spaces matter. I'll go through that in some detail. Non-normality matters if you're off-attractor. If you're non-stationary, then the eigenfunctions might not be orthogonal. So dealing with that is an important thing. I'll show you the Koopman-Schur decomposition. It's a new version of Koopman mode decomposition. All we need are time delays. The only thing that was used in that previous video are time delay embeddings. This is not always so, and you can lift with some nonlinear functions as well. But under certain conditions, provably, the spectra are computed correctly with time delays. Matt Colebrook will speak about limits and powers of Koopman learning in a moment here. And then I'll speak about some new applications. If you want to see a position paper, the operator is the model is a paper that I wrote for SAM News, and then there's one on arXiv that is a little bit more detailed on technical side. Okay, so let's go very briefly through the methodology. You have space, phase space or state space, M, I prefer calling it state space. You have functions, F, observables on M. We prefer starting with a space of complex functions for the reason that flattening of circles using neural networks is not a particularly appealing property of neural networks that are all real. The Koopman operator, of course, is the composition operator. Bernard Koopman invented it in 1931. There was a long history of using it in ergodic theory and somewhat in physics. But today we want to do, this is 15 years old, but still quite relevant. We want to understand flows like this, understand them, and then control them, as I've shown you in the previous slide. For a simple vector field case, I will emphasize here that smoothness is not a requirement. So you don't need to have a vector field. You can actually have measurable dynamics. That's how weak the assumptions are on this whole thing. But if you do have a vector field case, then it's f of x plus a of xu. This could be linear or nonlinear to start with, but you have a generator equation that you probably have all seen at one point or another, which is basically a reverse advection equation. The information doesn't flow forward, like in the Fokker-Planck, it flows backwards. Then if you take the right-hand side without the control, you have f dot grad phi for observable phi. That's the change of your observable in some direction. If you find a particularly good function, phi, such that ut phi is e to the lambda t phi, you call phi a Koopman eigenfunction. And Koopman eigenfunctions are useful. So we spoke a little bit about metastability and multiple bases of attraction. This is the standard map. Again, I don't know if you all see it, but it's a pendulum that's moving around in a plane, no gravity, well, like this. And then you kick it at periods, and it can have chaotic dynamics, or it can have regular dynamics. This is as multi-ergodic as you wish. And you can describe the invariant sets in it using the eigenfunction at lambda is equal to 0. At lambda is equal to 0, you have f dot grad phi is equal to 0. If you have a Hamiltonian system, that phi is energy. That phi is angular momentum. That phi is linear momentum. So all of the classical invariants are in the 0 eigenspace of the Koopman operator. But this map here is time dependent. It also has invariants, but they're not smooth. So nothing counters the property that you don't have continuous embedding. If you have something dissipative like van der Pol, here you can find two equations. One is for the angle, one is for the radius. These are the contours, and you basically do polar coordinates for a particular limit cycle. And then if you project, what did I get? Your velocity field on, this is not going, but it's the same movie as I've shown you before. If you project that velocity field onto the eigenfunctions, you get objects that are called modes. And here are the eigenvalues in that case of the jet that was streaming out. All this stuff here is continuous spectrum. If you're on unit circle, that means that you're stationary. You don't have any off-unit circle eigenvalues or eigenfunctions. Okay. So let me now go and talk a little bit about the theory itself. When do we have eigenvalues and eigenfunctions well defined, when we don't, continuous spectrum and so on? What is the underlying theory? And here I will connect it strictly with the classical dynamical systems theory. Here, and I would call it the Milnor form. Let's suppose that you have a compact invariant set. You have a physical invariant measure, means all of your continuous functions have time averages that are represented by that measure. You have the Hilbert space A, this L2. So that's on a tractor. I'm going to make it L2. You can make it negative Sobolev spaces or others. We are going to get real Polycott resonances and things of that sort, but let's work in L2. You can think of functions in that Hilbert space as defined everywhere. Think about the limit cycle and the phase on the limit cycle. You can propagate it backwards to be defined everywhere. So those functions can be defined everywhere. Now take functions on the attractor that are 0 on the attractor, analytic of attractor, and call that HB. Construct it somehow. We're going to append the unit constant function, because you need that for tensor product space, and work with that. You need a little bit of classical functional analysis, in the sense that the bounded operator is called scalar type if it satisfies that property. That is just a diagonalization property. If we got a spectral expansion for a matrix A, it would be sum of lambdas times the projection times eigenvectors times some constants. So that's what it is in infinite dimensional spaces. Construct the product space of these L2 functions on the attractor and analytic functions of the attractor. And then your Koopman operator is going to be the tensor product, is going to be a product operator on that space. And then we're going to define this, if we have sets A and B, the product of these sets is going to be the union of the products of points in it. Here is a theorem the reference is this. Interestingly, on this space, you can separately look at the eigenvalues on the attractor and off attractor. And all of the eigenvalues are going to be essentially the exponentials of the sums of these. For a van der Pol oscillator with a limit cycle, you find two principal eigenfunctions. One of them is complex with eigenvalue I omega, plus minus, of course. And then the other one has the flow k exponent lambda. So this is linear. But as, again, Eduardo pointed out yesterday, it is representing the nonlinear limit cycling dynamical system precisely, except of course at the point where phi1 is not defined, which is right here. But if you think about it, it is really an equation on a cylinder, right? It's not an equation R2. Well, these are not equations R2. It's a system that satisfies exponential evolution on a nonlinear space. So there is a little bit of a myth that we're getting linearizations, you know, in Rn, and then you can have only a single fixed points and so on. The reason why this is not true is that your embeddings don't necessarily have to be monotone functions of your original coordinates, right? And that's the essential kind of. Okay, so what do you get? By this theorem, if you have something that's limit cycling, in this particular case, it's a slightly different system. If you read off the imaginary axis, you're going to have your principal eigenvalues and then their multiples, like you would get in Fourier theory. And then to the left, if you have a stable limit cycle, you're going to get this pair, look, minus 0.3 plus minus 0.25. So this one and that pair, those are the eigenvalues, principal eigenvalues. Two of them are associated with the spinning. Two of them are associated with the convergence. And then you just multiply them by integers and add them up. And you're getting the whole lattice. So we understand that complete class of systems. You can call this a Koopman-Schur if you wish, not oscilloscope, because if you actually look at that lattice, you can tell what the system is doing. It's an oscillating system with an exponential decay towards the limit cycle. All right, for a large set of systems, we can separate the time average, the regular behavior, which is driven by eigenfunctions, and continuous spectrum. It goes back to 2005. Peter Schmidt discovered DMD independently in 2009. These things were connected in this paper in 2009. And so, just a small remark on the side, if you just put an expectation operator in front of your f, you get what is called a stochastic Koopman operator. Very similar expansion holds for a large class of these stochastic operators, and you get non-stationary stochastic process theory. Somebody has asked yesterday about how does this extend to stochastic systems. It's actually quite simple. You get pretty much a geometric theory of stochastic systems using this, because eigenfunctions tell you something about the geometry in expectation. But that's a different talk. Okay, so now a little bit more dynamical systems. Cell proved that if you have a normally hyperbolic invariant manifold and you have Cell-Sacker spectral conditions, then close to an attractor, you can write it as this skew linear system. Think of U as your angle on the van der Pol limit cycle phase, and think of Y as the transverse part. It's just that your matrix A depends on the value of your angle. So if you call that the cell type attractor, you can ask, well, what is that space HB of the attractor? It's interesting. You could start with something, and here I credit Mihai Putinar at UC Santa Barbara, because he told me, well, look at Fock spaces. Fock spaces have on the real line density that looks like that. It turns out that the Koopman operator does not conserve the Fock space structure, or it's not closed, so the Fock space structure is not closed under the Koopman operator except if the dynamics is linear. That's interesting. So this is a theorem that was proved by Putiner and a few others. So how do we actually construct a space that contains the function such that the Koopman dynamics preserves it? Instead of z, you put here an h, which is an eigenfunction. Eigenfunctions linearize. Oops. So it's normal that if the linear system doesn't preserve the structure, if the nonlinear system doesn't preserve the e to the minus z squared over 2, well, e to the minus h squared over 2 will, because that's actually associated with the linear part. That's how you get, well, with a little bit more work, and maybe many eigenfunctions, that's how you get these spaces that I called modulated Fock spaces, in which you get interesting results. So I just told you the story in 1D. So that h is actually the conjugacy or the eigenfunction at the lambda, which is the linearization at the fixed point. So your lambda is actually linearization of the fixed point. You can get it from linear analysis if you wish. Here we have this bistable system. Your h is going to be something that is singular at these fixed points, but it's actually valid everywhere else. Another misnomer is to say, oh, they're just valid inside the basin of attraction. This one is actually valid globally. It is discontinuous, of course, at the fixed points, because you cannot have a continuous embedding. But that provides you with a linearization in that particular domain. And if you think about it, this is mapping this finite domain into an infinite real line. So it has to extend to infinity, right? If it's going to capture all of this. All right. Okay, so let's now go and see whether this is machine learning and dynamical systems. So I spoke dynamical systems a lot. Let's see whether this is of any use. If you take your operator and construct a matrix out of it, which in this particular set of Hilbert spaces you can, your coefficients u1, 1, and so on, they're going to be the inner products of the action of the operator on the basis function inner producted with the dual basis. The basis functions don't have to be orthogonal. So it's u of j with gk. Now let's construct a compression, which essentially corresponds to taking that matrix and cutting off an n by n part of it. And let's ask what the associated coefficients are. And let's work in L2. It's easy to show, and that goes back to Yanis, Williams, Rowley, that formulas like this hold. This is a little bit different. It's a little bit more ergodic theoretic. But what I'll get your attention to is this is one basis function. This is the dual basis function. This is the composition with t, which is the operator. You're dividing by m when m goes to infinity. If you're dividing by m as m goes to infinity, you will never see anything but the stuff that is on the attractor. I started with L2, and I just showed to you that for dissipative systems, L2 might not be a great space to work in, if you're not sampling from many initial conditions with respect to another measure. So another limit that, again, Matt will talk about. So it can be remedied, but from a single trajectory, which you have in the case when you have natural systems evolving, you're going to see only attractor dynamics. Okay, how does this work in practice? You form a data matrix F that basically takes your observables and puts them in columns, and then you shift it one step forward, and then you say, let me take the F plus, which is the Moore-Penrose inverse, multiply with F prime, which is 1 times shifted. That's a matrix. Run it, see what you get. That's in L2. If you have another space, and in particular now the reproducing kernel Hilbert spaces actually come into the picture. Off a tractor, they are essential. On a tractor, L2 is enough. if you have a kernel, you're going to modify that formula. Pardon my notation here because I've replaced f with x. Just take that mental switch in your head. The G itself is this matrix here. And if you put G identity, you're going to get xt x inverse xt. That's more Penrose inverse. And then y is your f prime. Very, very similar. Again, just a matrix computation. But here is what we get with it. X dot is alpha x minus x cubed. Bistable. What do you expect for L2? You expect eigenvalues 0 because on a attractor, the attractor is the fixed point. So you can't get anything else but 0. There is no dissipation on the attractor, right? Indeed, you do a computation, and I don't think you can see this very well, but 0 is here. You see a bunch of points around there. That's DMD or EDMD. All these other points here are from what we call, Alex Mauro have called, and myself have called analytic DMD, where you set up the G correctly, and you get the correct eigenvalues. The crosses and the circles are almost the same, and so the eigenvalues up to order 5 or something like that are captured correctly. This is a dissipative system, and it's based on attraction. Slightly more complicated. I like van der Pol because it's actually, does anybody know what the van der Pol is the model of? Yeah, it's a tube, right? So my favorite tube product is on the left. I own one of these. It's an orange amp, if anybody is interested. It's the most beautiful guitar amplifier that I've ever seen in my life. But anyhow, this is the lattice of the type that I've showed you before. I don't know if you can see, but the crosses and the exact eigenvalues are here. This is the spread of DMD and EDMD, which is in L2. All right. So infinity matters was one of my 3 or 4 main points. Let's go to non-normality. If you're off attractor, you don't have normal eigenfunctions. If you're on attractor in L2, your eigenfunctions are going to be normal. You can orthonormalize them. If you're off attractor, there are problems. Take just a linear matrix A, which is a submatrix of the Koopman matrix in the linear case. Yeah, if you have a linear system, the matrix that pertains to linear observables is actually your standard matrix A. So if it's singular like that, and you perturb it by an epsilon, so 1101 or 11 epsilon 1, you get very highly well-conditioned eigenvectors. You know, in a situation where you actually have a 0 up there in earnest, like in a channel flow or something like that, you're going to get eigenvectors from a numerical routine, but they're going to be extremely poorly conditioned. Your spectral expansion is, of course, one spectral expansion is going to be wrong because that algebraic term T is not present in the output of what are just eigenvectors. If you fire up MATLAB, you're not going to get that 0. You're not going to get not dissing MATLAB, I mean Python or whatever you wish to fire up, right? And get your numerical simulation on. This is best seen in something like Orr-Sommertov flow between 2 plates, the eigenvalues in black, the pseudo-spectrum in colors. And you're seeing that the pseudo-spectrum itself is terribly conditioned, right? You just get little epsilons, different contours are different epsilons. You get these relatively small epsilons and things blow up. Non-normality, this is the product of eigenvectors, right? Eigenfunctions. And you're seeing off-diagonal yellows. That means that, so if you had orthonormal things, you will only have yellow and big value on the diagonal. You're seeing it off diagonally here. All right. So Schur form comes to the rescue. If lambda 1 to lambda are eigenvalues, you can construct a unitary Q and an upper triangular T. Eigenvalues of the upper triangular are actually on the diagonal, right? such that your A has a decomposition QT star, where Q is unitary. This is really nice because you don't have to compute the Jordan form, right? The benefits are quite nice. How do we extend this to an infinite dimensional situation? There is no diagonal, there is no nothing, right? Well, it turns out that this particular form on top can be written as a diagonal matrix plus the upper triangular part with zeros. That upper triangular part with zeros is nilpotent. So if you multiply it with itself r times, it's going to go to 0. This is normal. So that's what we're looking for. Under the assumptions that I have constructed so far, those product spaces, and in those product spaces, we can prove that the Koopman operator is scalar. So it has a diagonalization. In that case, the Schur form exists in the sense that your Koopman operator is a normal operator plus a quasi-nilpotent, meaning as you take its average multiplication to infinity, that's going to decay to 0. So that's the Schur form of a class of Koopman operators. You can prove a little bit more. Here, for the first time, I'm going to come to lifting. You choose, I kind of mentioned it before, but you choose observables in your state space. You say psi1 to psi n. And you do a finite dimensional projection. You can prove under these conditions that the sequence of approximations is actually spectrally inclusive. This goes through a resolvent analysis. I don't have time to dwell on that, but there are a few papers if you're interested as to how these things are incorporated together that I can show you. Now, the expansion, standard expansion of the Koopman operator goes lambda j, which is the eigenvalue, phi j, which is the eigenfunction, vj, which is the mode, right? The product of these is the Koopman mode decomposition. If you expand f in the Schur sense, where the first phi 1, capital phi 1, is just the eigenfunction, what the Schur computation tells you is, okay, get the eigenfunction, get another one, find a normal vector to the first eigenfunction. Get a third eigenfunction, might not be normal to the first two, find a normal vector, and so on. So your Schur vectors are going to be some finite sums of eigenfunctions, and then you can produce an expansion where CKs are what we call the Koopman-Schur modes. And this here is an exponential evolution, but not with a single exponent. Does this matter? So Koopman-Schur modes. And if anyone wants to look, this is with Zlatko Drmac on arXiv, hopefully published soon as well. Does it matter? So here is a data from Georgia Tech on a two-dimensional quasi-turbulent flow. You're seeing a snapshot on the left side, on your left side. You're seeing the EDMD reconstruction in the middle, and the top one looks good, but the bottom one looks really bad. The difference is that in one, the system was the Koopman operator was trained on the window size 70. In the second one, the only difference was it was trained on the window size 100. What happened is that the eigenvectors themselves became strongly non-normal. So you had them parallel if you actually computed over a longer time as things were kind of settling and converging. But you're seeing that if you're doing the Koopman-Schur reconstruction, you don't have that problem. So the robustness matters, and non-normality affects robustness, and therefore non-normality matters. Okay, so this is the kind of final part, except for the applications. Last time when I was here, I think I described in some detail what I call the representation eigenproblem. So it goes as follows. The operator is the model, so you have the operator U. For the soft robotics arm that I showed you, there is no model. So I'm saying there is an operator that drives the dynamics. It's in the background. Our goal is to somehow exhibit it, represent it. So you can ask, well, is there a finite set of functions? So this is a vector of functions and maps, possibly nonlinear, such that the action of the operator on that set of functions is a nonlinear map or linear map between that set of functions to its own space. This is a closure problem in Koopman form. Do we know solutions to that problem already? Sure. Not the same sure as in sure. The regular eigen problem is one of those things. If you find an eigenfunction, your capital F is just a linear scalar map. So any eigenfunction problem, standard eigenfunction problem, fits here. But here is a nice thing. You can ask, well, when do I have a linear representation? And the answer is very precise. If you have a point part of the spectrum, you will have a linear representation. If you have a continuous spectrum, you will not have it. But you can have a nonlinear representation. So you could find potentially a finite set of functions that are nonlinear that give you that. Now, is the representation always faithful? Do 2 points on the state space map into your representation? Of course not, but you can require it to be faithful. Simplest example of all time, you have a torus, you have a quasi-periodic rotation of the torus. You take two functions, z1 and z2, that are describing unit circles in 2 different dimensions. You multiply them by e to the I omega 1 and e to the I omega 2, and you get a linear representation of something that's evolving on a nonlinear object. So this is a message I took many times from Yanis, which is these transformations matter. Maybe that's lesson number 5, right? So these are linearizing transformations on something that is inherently nonlinear. Nonlinear dynamics on a nonlinear object that actually does have a linear representation. And the quest here is to find whether you have a linear representation or you don't. And you might not. It's all related to invariant subspaces of the Koopman operator, whether they are infinite dimensional 1 or finite dimensional 1. All right. You can play this game very nicely with van der Pol oscillator and ask, hey, for this particular equation, if I have just snapshots of x1 and x2, can I get a nonlinear representation? In this case, I actually have a point spectrum, but I will just play a funny game and say I'm going to embed with monomials x1, x2, and x1 squared x2, and I will find the submatrix of the Koopman operator, which is what the theorem is telling you. The theorem is telling you if you find a submatrix in which all the functions have functional dependence on each other, then you will have a nonlinear representation. So this is actually from a piece of software called PyKMD that's coming out soon, where you have where the system has essentially discovered that x1 at t plus delta t is equal to x1 of t plus delta t x2. So the coefficient in front of x1 should be 1. The coefficient in front of x2 in the first row should be 0.1 because my delta t is 0.1. 1, 0.1, 0. The nonlinearity doesn't matter in the first one. I started in 05, so maybe. In the second one, we have minus 0.1, 1.03, and minus 0.03. Well, the third point that I want to make is the time delays, x of t plus delta t is one step forward time delay, are all you need here besides this particular embedding, right? You don't need to estimate derivatives. So some of you might have tried Cindy or other methods that actually estimate the derivatives on the left-hand side. You actually don't need that. The embeddings can be purely time delay embeddings. And in the limit, you can discover the differentiable structure if there is one. This works for hybrid systems perfectly fine. All we need is time delays. This software that's coming, my affiliation currently is both University of California and AIM9. If anybody is interested, this is a modeling tool that you can use with a GUI, but I won't dwell on it. What is the model creation effort? The model creation effort is shown here. There are various even games that we can play with this particular thing in model games. I said it's hybrid, stochastic, if you wish. The model evaluation speed up over various other things is shown at the bottom. I won't dwell on it too much, but all of this is done essentially with laptop level power, which I care a lot about because the current approach to AI is a road to energy ruin. As somebody pointed out yesterday, we need a nuclear power plant to feed one of these models that are coming with trillions and trillions of parameters. It's silly, and our brain operates on, for better or for worse, on 20 watts. And we can do all this stuff on 20 watts. So laptop power is what we should, as a community, be looking for. And I claim it's possible. Not tomorrow, not 10 years from now, maybe 20 years from now, maybe I'll be gone, but I'm sure it's possible because it already exists, right? So I'll leave you with this final little movie. I don't know if it's gonna play. Probably not, it's a pity. But have any of you played the StarCraft game? Only a few, yeah. It's a different crowd. It's Zorgs versus Terrans, and you can play Zorgs versus Terrans with this methodology here. You don't need neural networks. The plots on the right are to convince you the accuracy of these techniques. They should be diagonal if your prediction is correct. This is the true outcome. This is the prediction. It's a stochastic, somewhat stochastic system. So you're getting, I would say, a very, very good, very good accuracy in this case as well. All right. I'll finish with the fact that, and this is some joint work with Yanis, that we have used this to model the dynamics of the coefficients of neural networks as well. I'll invite everybody to take a look at these papers if you have any interest. But the training itself is a dynamical system, so we utilize that particular idea. And I will finish with this particular picture. So the architecture for the modeling is you have an abstract state space, you lift it with observables. Your dynamics in latent space is provided by either a linear or nonlinear representation of the Koopman operator. You project down, that's your decoder. There are quite a number of papers. This is DeepMind. This is Gu and Dao at Carnegie Mellon and Princeton. Linear time sequence modeling on state spaces. There is no connection to Koopman here, but if you actually look at what they do, it's Koopman models. So a little bit more connection between the two communities is needed to realize this. And with that, I will finish. Thank you so much.